In this lecture today, I want to talk about the importance of mesh distortion and how it affects the Jacobian and how it affects the actual results of what we compute in a finite element analysis. So let's begin by go ahead and we're going to consider some three-node quadratic element. Okay, so let's give ourselves this is a quadratic element is going to have three nodes. So there's node. We'll call this node 1. Let's call this node 2. We'll call this node here node 3. Okay, so here's our element. And let's let this be the x-axis. That's supposed to be a large X. Okay, and then this will be our time axis, right? Okay, so there's time, and as deformation in time moves on, let's say this node moves to this location. Maybe this node moves to here, and maybe this node moves to here. Okay, so these are our deformed coordinates in our new element, right? So this would be, let's call this x1, x2, and this is a large X, and x3, okay? And I know throughout thus far in the lectures we've been using c as our current coordinate. I'm going to use little x here now because I'm not going to use big X through the rest of this derivation, and because I need to use c to describe my natural coordinates for Gauss quadrature. Okay, so this is going to be, try to remember, this is little x1, little x2, little x3, which in previous lectures we'd have written as c1, c2, and c3. But since we're going to talk about Gauss quadrature in this case, we need to have another label. So this location is our current coordinates. Right, and this location, this set of elements at time t equals 0, these are our material or reference coordinates. Okay. Okay, so the question is now how this is all pretty straightforward here, right? We just have a 1D element that's deformed. Now the question is, how does that deformation affect anything that we're doing? Okay, and what I hope to illustrate here is that it's significant. Okay, so in natural coordinates, right, if you remember, natural coordinates ran from -1, and we're going to use c to describe those, to 1, right? So we're going to map them to this natural coordinate so we can use Gauss quadrature. So if we do that, we can write the shape approximation as follows. Right, we would say that little x is a function of c and t, and that's going to be equal to ni, which will be a function of c, right, times xi, this nodal position vector, as a function of t. Let's call that equation 1. Okay. Okay, and the corresponding approximations can be written as follows. We can write our displacement approximation, if you like, as u of c of t is equal to the same sort of form, right? This is clearly an isoparametric element. So our interpolation functions times our nodal displacement vectors. Let's call that equation 2. And we could write our velocity vector in the same way. Of course, where vi now is our nodal velocity. Okay, and we'll call that equation 3. Okay, and let me just remind you, you had a homework problem where you derived it, but let me remind you what ni looks like for a quadratic element. So where ni of c is going to be equal to, this is just I'll write it as a row vector, 1/2 times c squared minus c. and then 1 minus c squared, and then 1/2 times the quantity c squared plus c. Okay? Let's call that equation 4. We're going to define that b vector term, right? Remember, b is the derivative of the interpolation function that we used. So we define bi of c, right, as follows. So remember, we had that bi, this is from our previous definition, was equal to ni, comma, and we use c, but now we're going to use little x here, so I'm going to put a little x there. And in order to make this as a function of c, we need to write this as ni of c times the partial of c with respect to x, right? Because we've defined ni in terms of c, so in order to do the partial, we need to use the chain rule on that. Okay, so what's this quantity? Well, that quantity looks like 1 over the Jacobian of that transformation. Okay, so let's just go ahead and write out in vector form what that looks like. That looks like 1/2 times this quantity del c del x, and now I have times the partial of ni with respect to c, right, which gives me, in this first term, it looks like I pulled the 1/2 out, so this just becomes 2c minus 1. Since I pulled a 1/2 out, this becomes negative 2c, but I have a 1/2 there, so we have to write it as negative 4c. And then this quantity becomes 2c plus 1. Okay, let's call that equation 5. So now we can define the rate of deformation, or the velocity strain. Right, and we define that as d, and I subscript it as a c, and now I'm going to subscript it with a little x, okay, as the quantity ni, comma x, vi, where vi was the nodal velocities, and I wrote that as bi, vi. So now I can use equation 5 in here and write that as 1/2 del c del x times 2c minus 1 minus 4c, and then 2c plus 1. Okay, now times our vector term, which looks like v1, v2, v3. Let's call that equation 6. And when we begin, we're going to consider the case where x2 is just at the midpoint, right? So we begin with x2 at the midpoint. Right, so what that means is that we could write x2 as the average of x1 and x3. So we say x1 plus x3 divided by 2. Call that equation 7. So going back to equation 1, we can write the mapping to natural coordinates as follows. Right, we could say that x as a function of c and t, right, this is equation 1, we said was ni xi, right, and we know what ni is, and also what xi is. That looks like it's going to end up being x1 over 2 times c squared minus c, right, plus x2 times 1 minus c squared, plus x3 over 2 times c squared plus c. Okay, and we'll call that equation 8. So I haven't done any substitution with 7 yet. This is just the mapping, right? Okay. Similarly, we can also write out the Jacobian now. So using 8, we may write the Jacobian. Right? We know that j is equal to del x del c. So if we do that, that looks like x1 over 2 just taking the derivative of equation 8, this is 2c minus 1 plus x2 times a minus 2c plus x3 over 2 times 2c plus 1. Right? Let's call that equation 9. Okay, so this is our Jacobian. Now we're just going to substitute equation 7, which gave us our value of x2 initially, right at the midpoint, into equation 9. Okay. If we do that, we end up with that j is going to be equal to x1 over 2 times 2c minus 1. Okay, and now I'm just going to go ahead and plug this in. This is minus 2c times the quantity x1 plus x2 divided by 2, right? That's what we had for x2. And then we have plus x3 over 2 times 2c plus 1. Okay, so you can kind of see we're going to get some cancellations here. And if we do just the algebra out, we see this becomes something very simple, x3 minus x1 divided by 2. That's what you would expect, right? That's the definition of the Jacobian. There's the length in the real coordinates versus the length in the natural, right? So hopefully that's pretty straightforward. So it's exactly what we expect. Call that equation 10, right? So what does that mean? Well, because, okay, so this says that because the Jacobian j is positive and constant, then we know that dx, right, the velocity strain that we defined in equation 6, let's go plug that value in. We plug in a constant value to this term here, right? This is 1 over j. Plug in a constant value there, and now we see that the velocity across the element must vary linearly, right? So this dx term varies linearly across the element as well. Okay, so all is well. There's no issues. Maybe in a previous class you didn't talk about what the issues might arise because you always solved everything on the original coordinates. But let's think about the case where we care about the new coordinates, where they may be deforming, as might be the case in a highly nonlinear problem. So let's just ask the question. Okay, what if during deformation, okay, x2 moves away from the midpoint? Okay, well, let's think about that. If that's the case, we could write that position as, we could say x2 is equal to, let's call it alpha x1, right, plus 1 minus alpha x3, right, for, let's say, somewhere alpha between 0 and 1, right? And at alpha being 1/2, right, that returns back what we got from equation 7. But now we're just saying let alpha vary, so that's going to be something that we can modify. Let's call that equation 11. Okay, so I'm going to substitute equation 11 into equation 9. And so I'm able to now write the Jacobian, which will now be in terms of alpha. So it'll look like x1 over 2. This term doesn't change, 2c minus 1. Now this term will change. This will become minus 2c. And now that x2 term, which is alpha x1 plus 1 minus alpha x3, right, plus x3 over 2 times 2c plus 1. Okay? You can go ahead and carry out the algebra. It's 3 or 4 lines down. I'm just going to skip, and I'm going to give you the conclusion. The conclusion is that it comes out to be x3 minus x1 divided by 2 times the quantity 1 minus 2c times the quantity 1 minus 2 alpha. Okay? Let's call that equation 12. All right, so let's just do a quick double check. Can we verify if I plug in alpha equals 1/2, which is what I said we had before, do I return the same answer? Well, alpha equals 1/2 drives this term in parentheses to 0, which drives this 2c to 0, and we're left with x3 minus x1 divided by 2, right? That's what we had for the Jacobian initially, which was constant, right? But in the case where alpha isn't 1/2, when that midpoint is not, or sorry, when the x2 value is not at the midpoint, then the Jacobian is not constant across the element, okay? So let me write that down real quick. Okay, so we verify in equation 12 that alpha equals 1/2 does return the Jacobian of x3 minus x1 divided by 2, right, which is what we want, okay? But for alpha not equal to 1/2, the Jacobian is going to be a linear function of c. Okay, why does that matter? Because this now opens the possibility that we could drive that Jacobian value to 0 or maybe even negative, right? Which is going to correspond to a 0 volume or a or a negative volume rather, right? Okay, so this opens up the possibility for J to be 0 or negative, which would imply a 0 or negative volume. Right? And we know this is not physical. So let's think about what it would take to drive that value to 0 or negative, okay? So we can look at this equation 12. We can see that the x3 minus x1 term is going to be positive, right? Unless well, there's no way for it to go negative. So that term is positive. So the only way to drive that equation 12, or the Jacobian, to be negative is if that 1 minus 2c times 1 minus 2 alpha term, if that term is less than or equal to 0. Okay? Okay, so that's the condition that we have. We can do a little massaging and just basically move this 1 to the other side and then multiply by a negative 1 and find that our criterion for that being negative is 2c times 1 minus 2 alpha being greater than or equal to 1, right? Solve that equation 13. Okay? When that occurs, our Jacobian goes negative, right? So let's just first consider the case where it goes to 0, right? Okay, so if that term, 2c times 1 minus 2 alpha, if that term equals 1, then j equals 0, right? So let's call this equation 14. This implies that j will equal 0. What happens when j equals 0? If we go back to our definition of velocity, remember there was the 1 over j term? What that would mean is that a j equals 0 term, that's going to correspond to some portion of that element, dx, going to infinity, right? Because there was a 1 over j term in that multiplier, okay? So 0 Jacobian gives us an infinite rate of deformation, which is again unphysical, right? So this is just going back to equation 6. Okay? So if I plot what I just drew for you there, that 2c times 1 minus 2 alpha, if I plot that line, I end up with the following. So looking at this plot that I've just given you, alpha here is on the x-axis running from 0 to 1, and c runs from -1 up to 1, right? And so this line that I'm showing you in the upper left quadrant and this lower right quadrant line, that corresponds to the j equals 0 line. And inside there, j is greater than 0, so the Jacobian is greater than 0. So maybe let's not say it's perfectly accurate, but it's at least feasible. Whereas outside this region, j is less than 0, it's negative, okay? So let me just note that here for you. Note. Okay, so for alpha equals 0.25, then j equals 0, right? At c equals 1. And for alpha equals 0.75, then j equals 0 at c equals -1, right? And these are the boundary nodes, right? So if that midpoint moves halfway to the other side, then the opposite boundary node has a Jacobian value that's at 0. Okay. So let me give you some remarks. Number 1. Okay, note that for alpha, anywhere where if alpha is between 0 and 0.25, right, or between 0.75 and 1, then the Jacobian is negative or 0 somewhere in the element. Okay, obviously that's not physical. So remark number 2. Remember that the Jacobian represents a volume mapping between real and natural coordinates. Okay, so if we have a value of j less than or equal to 0, that implies a negative density, which violates our conservation of mass. Okay, so you can start seeing the problems that are cropping up as elements deform. And this is just a little insight into the problems you're going to run into when you try to build models with nonlinearity. You're going to find that your model crashes because maybe you're running Abacus or something, and Abacus says, no, I can't do this. Now you're going to see, now you can begin to understand why that is. Abacus says, no, you have an unphysical problem. Now this mapping doesn't work. I have to shut down. Okay? Okay, so if we look at the Jacobian at the Gauss points, so if you had a first order, only a 1-point quadrature, you might have c equals 0, or more commonly, you're going to have maybe c equals plus or minus 1 over root 3, right? So that the Jacobian at these Gauss points may be positive and defined, but it's still solving a non-physical problem. Okay, so what that means is that just because you can evaluate the Gauss points and those Gauss points don't give you the values of the Jacobian of those Gauss points are greater than 0, that doesn't mean that you're solving a physical problem, right? And the last point I want to make, point number 4, and this is just a comment I'll make in passing, is that the effects of mesh distortion in 1D are less severe than in multidimensional problems. Okay, now I'm showing you the 1D case because it's easier to illustrate and we can clearly see where the Jacobian becomes negative. But if it's even possible to show that here, I just want you to be aware of the fact that if you're modeling in 3 dimensions, this issue of mesh distortion becomes much more severe. So it just this is the best case scenario. As we go to higher orders, it becomes more troubling. So it becomes important to make sure that Jacobian is not negative in the element so that we get accurate results.